So before I give you more examples, I want to give you the two last pieces of information that kind of fit in this section, 4.5, where we learn these new log rules. The first deals with something called the change of base formula. And the change of base formula, much as the name implies, allows you to change the base on different logs. First, let me give you the formal statement of the change of base formula. It says that if you have the log base b of x for any base b, and you want the base to be different, let's say, I don't know, c maybe, well, you can rewrite this as the quotient of two different logs that both have the base c. What you have to do is take the argument for this log and make that the argument for the numerator, and then you have to take the base over here and make that the argument for the denominator. What I'm saying is the change of base formula states that the log base b of x is equal to the log base c of x divided by the log base c of b, where c is whatever base you want it to be. So for example, if I had the log base, I don't know, 2 of 5. I don't know what this is equal to, right? I don't know what power I have to raise 2 up to make it equal to 5. I know it's more than 2 because 2 squared only gives me 4. But I know it's less than 3 because 2 to the third power gets me all the way up to 8. So it's some decimal in between 2 and 3. But what is it equal to? Well, I'm not sure. Maybe I could pull out a calculator. There's a problem. My calculator doesn't have a button for the log base 2. Or if it does, I don't see it right here. Well, that's okay. My calculator has a button for the log base 10. So I could just convert these into log base 10 if I wanted to. The change of base formula tells me that this is equal to the log base 10 of 5 divided by the log base 10 of 2. It's worth pointing out that this doesn't have to be log base 10. It could be any log I want. If for some reason I wanted this to be, I don't know, log base 5, I could say this is the log base 5 of 5 divided by the log base 5 of 2. I pick whatever base I want for the logs, and then I take the base and I put that down on the bottom as the argument. Think the base kind of goes down in the bottom here. And then the argument is what goes up top. Wait, the log base 5 of 5, isn't that just equal to 1? Yup. So wouldn't this just be the same as 1 over the log base 5 of 2? Yup. That's kind of interesting. The log base 2 of 5 is the same as 1 over the log base 5 of 2. Yeah, and that's true for any numbers, not just 2 and 5. When you switch the argument in the base, you're really just taking the reciprocal. And you could prove that fact. You don't need to have that fact memorized or anything. I just want to point out that there's this formula called the change of base formula, and it allows you to change the base on a log if you want to. The first justification I gave for this is calculator. If I want to know the log base 2 of 5, one way I could get there is I could ask my calculator, what is the log base 10 of 5? And then I could divide that by the log base 10 of 2. My calculator tells me that's equal to 2.3. Remember, this is supposed to be a number in between 2 and 3. 2.3, sure enough, is a number between 2 and 3. The log base 2 of 5 is approximately equal to 2.322. As you've seen before, this is not a proofs class, but I like to prove these things to you. So really quickly, let me show you how you can prove this change of base formula. I think it's kind of interesting. The method will be pretty similar to the way we proved things before. We're going to start out with the log base b of x, and we're going to give that a name. You can call it whatever you want. Maybe I'll call it n. Sure, why not? The reason I want to give it a name is because now I have a logarithmic equation, and if I have a logarithmic equation, I can change that into an exponential equation. I can rewrite this as b to the n power is equal to x. What I'm going to do now is I'm going to say, well, if this is the same as this, then the log base c of this must be the same as the log base c of this. So the log base c of b to the n power is the log base c of x. You might not see where this is going, but again, with proofs, often you're not supposed to see where it's going. Just make sure you can follow all the individual steps. How could I rewrite this line? Well, I have an exponent here. I'm taking the log of an exponent. I can bring that exponent down in front of the log and call it n times the log base c of b. That's my third log rule in effect there. And this n, which is now a coefficient, remember, that's just the name I'm giving for the log base b of x. So I can replace this n with log base b of x, and that gets me this equation. And now if I divide both sides of the equation by log base c of b, what I'm left with is the log base b of x on the left side, and on the right side I'd have the quotient of the log base c of x and the log base c of b, which is exactly the change of base formula that I was going for. Again, not a proofs class, I just think that's kind of fun. Before I end this video, I want to show you two log identities that'll end up being useful, and they come from the fact that f of x equals b to the x power and g of x equals the log base b of x are inverse functions of each other, right? This is how we defined these log functions. We saw this earlier when we were talking about the graphs. These two guys are inverse functions of each other. Well, maybe you remember all the way back from 1.7 that all an inverse function does is it sort of undoes whatever the function did. So for that reason, when you compose together a function and its inverse function in either order, whether it's f inverse of f of x or f of f inverse of x, either way, if you compose together a function and its inverse function, you're not doing anything. You're left with just this identity function. If you do this function and then you do this inverse function, you're right back where you started. If you do this inverse function and then you do this function, you're right back where you started. The composition of a function and its inverse function is just the identity function. And so because these two functions are inverse functions, if I compose them together, I must just get x. So if I take g of x and I put that inside this function f of x, I'm getting f of the log base b of x. So I'm copying my formula here for f of x, except I'm replacing all the x's with what's in these parentheses of the log base b of x. I get b raised up to the power of the log base b of x. But because they're inverses, that must be equal to x. This right here is the first of the two log identities I wanted to show you. The second one, you just compose these two functions together again, but now you do it in the other order. Now I'm taking g of f of x. Well, f of x is b to the x power. So g of f of x is just copy this equation for g of x, except replace all the x's with whatever's in these parentheses. I would get the log base b of, and then instead of writing the letter x, I'm going to write what's in these parentheses, b to the x power. This is also equal to x. If you're really clever, you might notice this is a fact that you already knew, right? You don't need this as a new identity. You could have just taken this x and brought it down in front of the log using your third log rule, and you'd have x times the log base b of b. But the log base b of b is always 1 because it's asking you what power do you got to raise this b up to make it equal to this b. That's just 1. X times 1 is just this x. Or you could just look at this and be like, wait a minute, the log base b of something, that's asking me the question, what power do I have to raise b up to make it equal to b to the x power? Well, obviously this b would be needed to be raised up to the x power to make it equal to this b to the x right here. So the log base b of b to the x, of course that's x. Similar logic yields this identity as well. It's just a little bit harder to see. What the log base b of x is an exponent. It's the exponent that you have to raise b up to make it equal to x. So what I'm doing is I'm raising this b up to some exponent. And that exponent I'm raising it up to is that magical exponent that b needs to be raised up to turn it into an x. So I'm raising b to this magical exponent that changes b's into x's. Of course, what it's going to be equal to is this x. These are both facts that you may have already kind of known without even knowing that you knew them, but writing them more formulaically like we have here will be really useful going forward. So I wanted to write them both down for you. These are our two new log identities. Those and our change of base formula is the end of the information that you need from 4.5. I'll make one more video just kind of showing how to use these guys and what we learned about our log rules when we have variables floating around in here, and then we'll be done with the section.